So we've looked at optimization, one of the key applications of differentiation. This is where we use differentiation, set it equal to 0, and we calculate the maximum and minimum values for a situation which allow us to get the best possible values for whatever the scenario is. What I'm going to do in this video, I'm going to set you a couple of questions. I want you to pause the video, have a crack at them, and then come back and check your answers. So the first video is all about a theme park. It uses vehicles to transport visitors around attractions. The cost of running these is given by this equation here. C equals 400 over V plus 25V plus 50, and then at V represents the speed of the car. I want to know what speed the car should travel at in order to minimize the cost per day, and what is the cost of running the cars in this scenario. Second one, IKEA store, wonder who I based that on, has designed a rectangular coffee table with a glass top of length X centimeters, breadth Y, and a perimeter of 360. I want you to first find the expression for the area of the table, and then what value of X gives the maximum area, and what is that area. So, pause the video, have a crack at these. So the first one is the theme park question. So here's my equation. I want to minimize the cost. As soon as you see something like that, so what is the minimum, what is the maximum, instantly think of the derivative. We have to take the derivative, set it equal to 0, and solve it to find the value which gives us this. So first thing I need to do is write this in a form which I can take the derivative of. Now 25V, I could take the derivative of that. 50, I could take the derivative of that straight up. This one here, I have to write it up there. So I have to then say that C of V equals 400, and write it with a negative power V to the negative 1, plus 25V plus 50. Now that I've got it like that, I can take my derivative. So I get C dash to V equals, bring the power down, negative 400, reduce it by 1, V to the negative 2, plus 25, 50 just disappears, and I know to minimize it, set it equal to 0. Set it equal to 0 and solve this equation. So I get negative 400 over V squared equals negative 25. Shift the 25 down and the V squared up, and I get V squared equals negative 400 over negative 25, which gives me 16. So V squared is 16, take the square root, and I get V equals plus or minus 4. Now again, this is the point where logic comes into play. If I take a negative V here, it's telling me I've got a negative speed, something we can't have, so I can drop the negative 4 value, and I can say fine, so I know then that V equals 4. So I've got the speed V, which I think minimizes it. What I now have to do is prove that it minimizes it. So I have to use the table of values in order to do that. Now, remember what we said before. When we set up the table, we have to put it into the context. So our top line stays the same. There's a stationary. I look above it and I look below it. So 4 from below, 4 from above. When I'm setting up the table, my context is C dash to V. So you have to put that in your derivative line. D by dx will not get you marks for this. Put it into the context of the question. Then I can look at what the graph looks like. Now at 4, I know my derivative is 0, so it's flat. If I approach it from just below it, so let's say something like 3, what I end up getting is negative 400 over 3 squared, so maybe negative 400 over 9, plus 25, and what that gives me is that gives me a negative value. 400 over 9, or a value that's below 4 squared, is going to be bigger than the plus 25, so it's going to leave me with a negative factor, so it's going to be negative. So it's going to be coming down. If I look at 4 from above, so let's say 5, I've then got negative 400 over 5 squared, so negative 400 over 25, which we know is negative 16. Negative 16 plus 25 gives me a positive value. So anything above it, I'm going to get a positive value. So my graph looks like that. So I can then say is therefore V equals 4 gives the minimum. I know that that's going to give my minimum per day for the cost. What I can now do is substitute it in and calculate it. So my minimum cost is given by C of 4, which is 400 over 4 plus 25 times 4 plus 50. 400 over 4 is 100, so I've got 100 plus 100 plus 50. So therefore my minimum cost, C of 4, equals £250. That's the minimum cost of running these cars per day. If I run them at the minimum speed, at the maximum speed, v equals 4. That there is how we work a question like this. So using the minimum to get the cost that we're after in this scenario. The next question was looking at the store with a rectangular coffee table with a glass top. Now this one starts by getting you to find the expression for it before you then go on to look at maximum or minimum. Now the example we did in the previous video looked at something like this where you had to come up with the expression. Now a lot of the times you'll get something like this where you've got two variables started with your area, then you'll get some other property that you have to use. Now let's start with the area of the rectangle. Let's start with a of x, let's call it that. Now we know that for the area of a rectangle, it's length times breadth. So in this case, it's going to be x times y. So what I end up getting is xy for my area. Now, the y we want rid of. How do we do that? Well, this is where the second property of the perimeter comes into play. Now think of the rectangle. A rectangle is going to be like that. I've got a length of x and I've got a breadth of y. To get the full perimeter, I've got 2 of the x's and 2 of the y's. So I then know that 2 of the x's plus 2 of the y's is my perimeter, which is 360. From that, I can make an equation to get rid of y. So I know then that 2y equals 360 take away 2x, divide everything by 2, and I get that y equals 180 minus x. Now that I've got that, I can substitute it back into there. What I can then say is a of x equals x bracket 180 take away x. That there is my equation for the area. We've got what we want to know. The second part, so part B, is what value of x gives the minimum area. Again, the maximum area, sorry. Again, looking at that, maximum derivative optimization. So first thing we have to do is make sure we can take the derivative, so I get rid of the bracket. So I get a of x equals 180x minus x squared. Now that I've got that, I could take my derivative, set it equal to 0, solve it, and find the value of x which I'm after. So a dashed of x equals 180, reduce the power, bring it down, minus 2x. And I know for the maximum area, set it equal to 0. Now we solve it. So I get 2x equals 180, so I know that x equals 90. So for my maximum area, x has to equal 90. But we have to still prove it. So this is where again our table of values comes into play. So we know that x is 90, we want to look above 90, and we want to look below 90 to see exactly how it happens. Now remember, in your table of values, your second row, put it in the context. In this case, our derivative is a dashed of x. That's what goes in that row. We then still keep the graph at the bottom. Now we know at 90, this is going to be 0. So my derivative is 0 and it's flat. If I look at 90 from below, let's say 89, I've got 180, take away 2 times that. Well, any value below 90, 2 times it is going to be less than 180. So I'm going to end up with a positive value, which means that my graph's coming up. Any value above 90, the 2x is going to be greater than the 180. So when I do 180 take it away, I'm going to end up with a negative value, which means it goes down. So what that then means is I could say, therefore, x equals 90 gives the maximum. We've proven it. We've used our table of values to show that this is the maximum turning point, i.e. the maximum stationary point, so the point that optimizes it the best. So x equals 90 gives that. We now want to find the area, substitute it into there. So I want to find a of 90, which we know is going to be given by 90 times bracket 180 take away 90, which gives me 90 times 90, so I've got 90 squared. So my a of 90, my maximum area, equals 8,100 square centimetres. That there is the maximum area you can get for a table from that shop. And again, it's the same set of steps for any optimization question we have done. Sometimes it'll ask you to calculate the area or a formula or an expression. That's where part A comes into play. You'll get a couple of properties, use both the properties to get what you need and get rid of variables. So we got rid of the y here by using the second property to get an expression for it. Once you've got that and it's asking you about the maximum area, remember those are the keywords you're looking for: maximum, minimum, highest, lowest. We think, right, derivative. Get it in a form you can differentiate. Take the derivative, set it equal to 0 and solve it. Once you've solved it, use logic if you've got a couple of values. So the previous one we had a plus and minus 4, we can eliminate one of those, and then use your table of values like this to show it's the maximum or minimum for the context. Again, remember this part here. Make sure that this bit, this line of your table of values, is in the context of the derivative. Don't just write d by dx. For this one I wrote a dash of x. Write it in the context of the question, because that will cost you a silly mark regardless of whether your table of values is right. And we don't want to lose marks for something as silly as that.